Welcome to the HiRSE Seminar Series on Research Software Engineering in Helmholtz and beyond.
Okay, so yes, we're going to be talking today about MELT. This is a process and an infrastructure for test and evaluation of machine learning models that we developed here at the Software Engineering Institute. So we have one quick slide there. And the general format we're going to go through, we're going to talk about some background and motivation for the tool itself, our current and future work, a quick summary, and then just some references at the end for all the relevant information. So we'll start with the background and the motivation of the tool. First, a quick background of Carnegie Mellon Software Engineering Institute, which is where myself and my team works. We were founded in 1984 as a DoD Research and Development, federally funded research and development center, which is almost always shortened to FFRDC. We are administered by Carnegie Mellon, so we are all technically Carnegie Mellon employees, and we work under them. So our portfolio as an SEI as the whole connects software, cyber, and AI strategies. We have three separate divisions, which are focused on one is software, one is cyber, and one is AI. My team, we all fall into the software division, so that's where we are focused. We have about 650 employees. We are headquartered in Pittsburgh, Pennsylvania in the US. We also have smaller offices in DC and then one also in California. So, MELT, which stands for ML Test and Evaluation. So MELT is a system-centric, quality attribute-driven, semi-automated process and infrastructure that enables the negotiation, specification, and testing of ML model requirements. So MELT provides evidence of testing activities that can be shared with model acquirers and integrators to inform integration and test and evaluation activities. We co-developed this tool with Army AI2C, which is the Army Artificial Intelligence Integration Center, as part of their model development process, and we have started implementing it with them, and we have seen very positive feedback and results. The tool is open source and is available on our GitHub at the GitHub MELT team MELT repo. So if we look over on the right on this diagram, we can see kind of a quick diagram of how MELT is structured. There are several different parts to it, all focused around the negotiation card. So that is where all the information for the tool is stored, or a large part of the negotiation information, and that will then inform the rest of the tool and the process. So we start with stakeholder negotiation on top, and that is kind of the general stakeholder negotiation you would have in any ML model development process where you're talking with the stakeholders, you're getting requirements, and you are going to be seeing what is the goal of the model, what kind of model we're looking to use, and all of that kind of stuff. This then will feed into the internal model testing, which is the model testing and development you'd be used to as a model developer, where this is you are fine-tuning your parameters, your hyperparameters, you are making adjustments to the model, and you're getting to the correct baseline. So that also feeds into the negotiation card. And then we will get into later the system-dependent model testing, which is where MELT starts to help with testing, and it can help produce artifacts so that people who use your model can be more confident in it, and then they will have reproducible tests to make sure that you are providing them with what you said you are, or on the flip side, you are receiving what you were told that you were receiving. So this is a quick diagram of the entire MELT process that we will break down as we go. Just know that it starts up here at the top again. So we have our system stakeholders and our model development team, which is where we're doing the first step of continuous negotiation. And this is where you are talking with the stakeholders. Again, you are determining what kind of model you're looking to do, what are the baselines you're looking to exceed, what kind of data will be available, and so on. And then we will work our way through the rest of the process in a further example shortly. So MELT has four main use cases, two of which I have mentioned. So the first main one is model testing. This is where model developers would use MELT as part of their development process, using either the front end of MELT, or you can integrate it into your development pipeline using the library part of MELT. Second, we can do model acquisition. This is where organizations require contractors to use MLTE as part of their development process, and they would submit evidence for reuse or reuse in the internal model testing, development test, or operational test. We can do model onboarding. So model organizations use MLTE to evaluate off-the-shelf models for fit with use cases, or we can use it to analyze the differences between two options and do analysis of alternatives. So this is where organizations would again require the vendors to use MLTE when submitting proposals, also known as models, such that the test evidence can be compared between vendors. So MLTE has these four main use cases. It's all the same tooling. It just depends how you want to take advantage of it. Because again, if you are trying to develop a model for yourself internally, you still want to have a robust testing practice so you could use it yourself, use the model testing. Then if you develop new versions of your models, you can run the same tests, compare between them more robustly than just kind of having one-off tests or just field tests based on how you think the model's performing or a couple quick benchmarks. And then it's always been a problem that when you're acquiring a model, even if the contractor who you're acquiring it from says that it works up to a certain baseline, that's not always going to be the results you're going to see. And so by having Melt be a part of this process, you can have them give you the baselines that you would expect normally, then also provide test data from Melt that you can then repeat and verify that it is passing all of your metrics past just a performance baseline. And that will include things like how robust it is to blur, how safe the data is, and other things. Everything else that goes into what makes a model work in production. So, a quick piece of terminology. We are going to be talking about things in the context of an ML-enabled system. So we see an ML-enabled system as a software system that relies on one or more machine learning based components to provide the required capabilities. So a lot of times when you're thinking about machine learning, you are only thinking about the trained model. So we have the trained model that produces an output or is consumed by downstream components as just a piece of this ML component, which all of these go together to form the piece of machine learning and the capability that you're going to be creating. So we see all of it as very important and should be tested and monitored, not just the trained model. So we see here parts that we include in this system. We have upstream components that are going to be providing production data that will then feed into our ML component as a whole. And then this ML component as a whole includes the data pipeline to process this data to be ready to go into the model. That will then transfer directly into the model. The trained model will do its evaluation, its manipulation. Optionally, there is post-processing on this data if there needs to be. And then there is some insight, prediction, and inference that can happen after this, and this will feed into the downstream components. So in this context, where do the ML requirements come from? So system decomposition into components happens during the system level architecture and design. So we see here we need to separate directly the ML components from what it's a part of, which is the ML-enabled system. So some of the components will be ML components, and they'll derive requirements from the system. So just because you have your model and it has certain inputs, if the inputs coming from the system are different, one of them will have to adapt. And this will most likely be in the model in this case. And so we will have to derive these input data types from the system, and that will feed into our ML component requirements. Similarly, the results of the test and evaluation components inform these system level activities. So if you have your model, you get the requirements from the system for what data you're going to be taking in, and then you'll have a certain output type, a data format, depending what kind of model you are running. And that will then impart requirements onto the system because you then are outputting a certain type of data, and the system will need to be able to handle that. Which again just makes the component a part of the system, and it really does require and rely on each other in order to function. We cannot treat just the model as the entire ML process. So we're going to walk through an example to kind of get an idea of how we would use MELT, and we're going to focus on something I mentioned before, which is the quality attribute scenarios, which is what we are going to be using to elicit these requirements and really to structure the discussion about how we want to build this model and how we want to evaluate this model. So in this example, we are going to be talking about an example model which would be used to identify flowers as you walk through a public garden. So the system uses an ML component for flower identification. So we have the system as a whole, which will be taking in the images, doing any processing on the images, and then feeding it to a machine learning component that will then be identifying the flowers to tell the user what kind of flower they're actually looking at as they walk through the garden. So we are going to look at this diagram again. In this situation, this is our requirements. We're looking to make this flower identification. So the process would start with the continuous negotiation. So the model developers and the system stakeholders would initially meet, and they would fill out and decide what they want this model to do, how they want it to fit into the overall system, and what kind of baselines we're going to be having. So we start with the continuous negotiation. And this happens throughout the process, but we have to have one big discussion at the start to really just get a baseline for what we're looking to do. So very often, the component developers do not receive any system context when they're asked to develop a model. This happens a lot, especially in organizations with separate data science teams, and this leads to something that we call ML mismatch, which is when the developers end up creating something that fits for how they view the problem, but once you get into the system context, it really doesn't line up with the goal of the system, and then will ultimately cause ML mismatch and lead to failures within the model or in the system as a whole. So not surprisingly, testing is limited to the statistical tests related to model performance. Continuous negotiation between the ML component developers and the system stakeholders ensures that the system context is shared. The ML component development and testing is guided by the system context, and test results drive potential changes to requirements. So again, a lot of the time when you are going to be developing an ML model, you will get a couple metrics, very high level, I need to be accurate this percent of the time. And honestly, sometimes that's all that you get. And so as a model development team, that is usually not enough information. And then again, we will get a lot of ML mismatch because you will develop a model specifically to reach that baseline. But then once you get into the system context and try and integrate into the system as a whole, there will be gaps, and then either the component will not work at all, or you will see very degraded performance. And so part of continuous negotiation is eliciting all of these system level requirements up front so that as the model is developed initially and then iterated on, you can get better results and have less time, spend less time going back and reworking things. So this requirement elicitation is driven by quality attribute scenarios. So what is a quality attribute scenario? The quality attribute scenarios guide the elicitation and the documentation of system required components. So a way to specify a system structural and behavioral requirements, known as quality attribute requirements, non-functional requirements, or system qualities. So the goal here is to ensure that the quality attribute requirements are described unambiguously and are testable. And this is key because if you just say, I want my model to work fast, and that is your quality attribute scenario because I want my users to have a really good time in my garden, I want them to see all the flowers, and I don't want it to be loading for minutes at a time. You can say that, but if you just say, I want it to be fast, that is not something that you can really test without a strict value. And fast it will be different to everybody. So these scenarios can be used during model development to communicate and negotiate with stakeholders. You can guide the model design decisions, and you can reason about trade-offs that will need to be made. And then finally, and most importantly for MELT, we'll be building test cases that can ensure that these requirements were met. So once we've done this, we will have our initial discussion of what kind of model we're going to have, and then we will have defined scenarios in which we define how the model is going to perform in these scenarios. And then we'll talk about how we would define this in a QA scenario specifically. So there are 6 parts that we would talk through when we are defining a QA scenario for a model system, for an ML system. So we start with the source of stimulus. So this is what is going to happen that will trigger this event that we want to be monitoring. So stimulus is a condition arriving at the system. The source of stimulus is where the stimulus comes from. The environment is what set of circumstances the scenario is taking place. So are we in normal operation? Are we in really high CPU use? Or is there startup development time, etc.? Then we have the artifact, which is the target for the stimulus. The response, which is what we want to happen when we receive this stimulus. And then we have the response measure, which measures used to determine that the response really achieved the scenario and we got the right output in the certain scenario. So an example for the garden buddy, or the garden buddy for the flower identification. So if we were here and we were the stakeholders, we might say that we want this model to be robust to image blur, because we know that people are walking around while they're in the garden. They might not always stop completely and get the best image. So it might be blurry. They might not have the nicest camera, and they still want this component to work nicely and to identify the flowers for them. So in this case, the stimulus would be that the ML component receives a blurry picture that was taken at the garden. The source would be the flower identification application, which would be our ML system. Then the environment is just normal operations. It's nothing's going on with the operation, or there's no really high CPU use or anything, just normal operations. The artifact that we're going to be testing here is the ML component. And the response is that we want to successfully identify flowers. And then how we're going to measure this response is we want to have the same rate as non-blurry images of correct identifications. So we've gone from what could have just been, I want this model to look at blurry images and say, I still get a correct identification. But now we have it structured a little bit better so that we know all of the parts of the scenario when this will need to be happening. And then we can build test cases around this, and we can use this to better define the ML component as we do model development. So once we have defined all of these quality attribute scenarios, there will be several for each model. We're going to look at one today. Then once you have all of these, you have basically defined what you want your model to be doing under what circumstances, and any different odd circumstances you can get into, so you know what you want your model to be doing under every scenario that is important to your case. So then we are going to be using the negotiation card. This is what we use to record agreements, and it helps drive model development and testing. So simply, it is basically a form that you will fill out with the system stakeholders and the model development team. There are several pieces of this, which we'll be talking about. And it helps guide the discussion, again, because a lot of times during model development, when you get requirements, these requirements will often be very vague from these stakeholders, and they will not always be actionable. And sometimes you'll just miss important data that you will need to develop these models, and then you'll have to go back to the stakeholders, have more meetings, and so on. So the goal of the negotiation card is to focus these discussions and help you elicit all of the requirements that you would possibly need in order to develop a model. and it will help to get you to a point where you can build this model without having to go back and forth too many times, or it is less than what you would normally. So our negotiation card was inspired by model cards and data sheets for data sets. Its goal is to record the outcome of stakeholder discussions related to the system context, and it can be revised at any point during the model development and testing process because we acknowledge that model development is very iterative. And even if you do use this negotiation card and get all of the requirements set up front, there's always going to be changes. You're going to be iterating. And so you can come back and adjust this as needed during the development of the model. So there are a couple of major sections to the negotiation card, which we find to be very important in the elicitation of these requirements. So we start off with the system context. This is where we talk about kind of the overarching things that the model is going to be looking at. What is the task of the model? What do we actually want to be doing? What are the technical goals and what are the business goals this model are going to be fulfilling? What is the uses context? How are we going to be using it? Where is it going to be used? And then we want to know about any false negative and false positive risks so that when we're making the model, we can account for those. Next, we have the data section. So this is where you'd fill out anything that you have, any information you have or would need about the data set. So we have the data set as a whole, what data set, if you're using one from online, where are you getting it from? What is the distribution of it? What are the labels that are applied to these data points? And what is the schema of the data so we know how to feed it into the model. Then up next, we have the model section. This is where we're going to be talking about kind of just the specifics of the model in the terms of resource usage and how it's actually going to implement into the system. So we're going to be looking at the training compute resources, what deployment platform we're going to be using. So is it going to be on a local server? Is it going to be on a cloud server? Will it be like we are talking about with our current scenario? Is it going to be running on someone's phone potentially? Or will that be communicating with a cloud server to get data back? And then we have the capability deployment mechanism. Is it going to be, again, using an API? Will it be user-facing? And then we have, very importantly, the input specification and the output specification. So when you are actually running this model, what specific data points are you going to be taking in to make these predictions? And what are you going to be producing as a result of these predictions? And then lastly, we're also going to be looking at the production compute resources, just so we know both during training and during testing what kind of requirements or limitations we're going to have and what we need to make this model fit under. Because again, if you want to run Garden Buddy on someone's phone and you want the model to be running on their phone, you're going to have very strict production compute resources. You're not going to have a lot of resources available there to run the model. And if you do not know that when you're developing the model, you may produce a model that will just not work properly when running on a phone if you're expecting it to run on a cloud server where you have lots of additional GPUs and so on. Lastly, we have the system-derived requirements as the last section of the negotiation card. And this is where we're going to be basically filling out a bunch of quality attribute scenarios. And this is, again, where we would, like we talked about before, with the quality attribute scenario, we have a specific scenario. We lay out what kind of stimulus we're going to be receiving, and then we want to list how the model is going to react to this, and we're going to be using those later to create test cases. So the next step is the internal model testing. So this is not MELT specific. This is actually just a name that we have for basically how you would develop a model outside of MELT. So this is where you're going to be developing the model, you're going to be collecting performance metrics, you're going to be comparing against your baseline, and then you're going to see if your model exceeds that baseline. So this is basically just the iterative approach of you producing a model that almost everyone follows, where you're just adjusting hyperparameters, testing data, doing everything that you need to make your model fit and exceed the initial baseline that you have. The difference and benefit of using it while using MELT is we are going to have all the information from the negotiation card available to us while we are doing this internal model testing. So we can see if we're, for example, looking at the training resources section or the production resources section. If we start running the model, we train it all up and we have whatever massive amount of training resources available. That is great. But if we then are running the model and it is using a very large amount of resources, but our production resources from the negotiation card is very low, we're going to have to make adjustments there. And then this would all happen during internal model testing. So if at any point something needs to change, you can always go back and renegotiate this negotiation card with the stakeholders. But in general, you would be using information from the negotiation card, developing the model, and then you would be, once you have that model meeting the baselines and meeting the requirements from the negotiation card, we move on to the next section. So, as I was kind of talking about, this is testing that occurs as part of model development, which is kind of the base model development that you'd expect. It recognizes the experimental nature of model development because you're going to be making iterations. There's going to be changes. You're not going to get it right on the first time. So you're going to have to adjust hyperparameters and you're going to have to make different changes to the model. So this ML component design and development decisions are informed by the negotiation card. And this is the benefit of doing this within MELT. Ideally, you have a lot more information available to you while you are developing this model so that you can get a better result the first time when you try and move past this step. And the end cases for this internal model testing is the model performance exceeds the baseline, or more information that requires more comprehensive testing is needed. And so when either of those are met, we will move on to the steps 5 and 6, which are the SDMT and then the test cases. So SDMT and test cases, and along with the testing evidence, which will be happening at the end from these. So SDMT, this is where MELT really comes in the testing sense. So this is once you've done your internal testing, again, you've kind of worked up your model to exceed a baseline, you think you have something good, you can then move on to the system-dependent model testing, where MELT will help you create test cases, and then this becomes the artifacts that you can pass on along with your model to say, these are the tests we ran, and then they can be reproducible for other stakeholders or the people you are acquiring models from. So, SDMT, it focuses on obtaining evidence of satisfaction of system-derived requirements. The goal is to collect evidence for each system-derived requirement in the negotiation card. So again, these are our quality attribute scenarios. So it requires translating these QA scenarios to ML component test cases. So in MELT, each test case is defined in a test suite, and it includes the QA scenarios associated to that test, a measurement to gather evidence, and a threshold and validator to define success. So the whole goal of this section is we are going to, again, produce reproducible test cases that can be ran on the model. And the goal of each of these test cases is going to be fulfilling a scenario that we elicited during negotiation and made these QA scenarios. So back in our quick QA scenario, we were looking at robustness to image blur. So in here, we can look on the right that we have, on the left, we have the defined test specification. We have a QA category of robustness, which is, again, is derived from the QA scenarios that we made earlier. We have a subsection. We are looking for robustness to image blur. And then as part of SDMT, we are going to define a measurement that we will use to define whether or not this is valid and passed. And then we will have a validation metric, which is if it is, in this case, below 0.05, we will consider that a passing of this test case. And this will happen for every quality attribute scenario within your negotiation card, so that again, at the end, we'll have the output of all of these, and then we'll form a MELT report. So In this demo, we would have the measurements for each test case in a separate Jupyter notebook, and we are going to be using the MELT library to set up the data, run the measurements, and collect evidence, store this evidence in a store, and then later all the test cases are validated using the stored evidence against their specific validators. So very importantly here, we have the mapping the QA scenarios to the ML component test cases. So this is another example of how we're going to be setting up a QA scenario. So the stimulus, again, we have the data in the data source. We have the source of stimulus. We have the context. We have the artifact, which is going to be our ML component we were looking at. And then we have the response and response measures. So this is kind of what we have as the ML test code that comes out of this. And this is kind of what we're going to be writing during SDMT. So we need to be identifying the data sets that meet the specified characteristics as stimulus. So if we're going to be requiring a blurry image to test our model, we need to have a data set of blurry images to use. We have to be able to generate or transform that data to directly work into our model. And then if there is specific context, in this case, there was not, as we were operating under normal conditions, but if there were any additional conditions that needed to be part of this scenario, we would replicate them here during that test. We would then pass all of this into our ML component. It would run and produce an output. And then we would look at our response measure and such, and we would look at, does it meet the response measure? Do we get the test set up and everything correctly? And then we have to make sure that we have the conditions set for the test to pass, so we know if everything worked correctly. So this seems like kind of a lot of testing that we're going to be doing, and it's going to be very specific to MELT. So one thing that we have included as part of MELT is the test catalog we're going to be talking about next. So because MELT is very specific, the test cases have to work within the MELT framework. It can be a bit overwhelming, and we understand that. And also, as you're using it within a organization or within a team, you want to be able to benefit from tests other people have written and just share the knowledge. So that is where the test catalog comes in. So the test catalog contains reusable examples of test cases organized by quality attribute. It is defined by a quality model for ML components and is embedded into MELT. And the default test catalog contains examples for each quality attribute. So while you are developing, if you get to a starting point, and you don't know how to test a certain model or a certain scenario for that model, you can go to the test catalog and you can see if there are any examples. So if you were going through one of our MELT demos, each of our MELT demos that is included in our repo has test catalog entries for each test that it has written. So each of these test catalog entries includes what quality attribute it's looking at, some additional data for what kind of model is being used, and gives you a test code snippet for how you would integrate and use this within SDMT and MELT. And so the idea is you would start with your MELT instance, you would use some of these to kind of get started, and then as your team builds upon them and you continue using it, or alternatively as an organization, you could host a MELT instance. Then as you use it more, your ML component developers will contribute to this test catalog to create an organizational test catalog. So over time, the test catalog will contain organizational knowledge of how ML components are to be tested. Because sometimes testing certain pieces of an ML component is very difficult or very niche. And so the test catalog allows you to share information, provides examples of how you would test these, and then continue to iterate upon them and provide them for your team or your organization as a whole. So looking again at some quality model for ML components, these are all the quality attributes that we have identified. And so we have 7 categories. We have the categories of behavior analysis, confidence, consistency, continued operation, maintenance and evolution, responsible AI, and security and privacy. And so this is the result of a lot of research and a lot of work from my team. And these are the things that we see as very important for ML components. These are the subcategories, and these are how it would break down. So if you ever say, I need my model to do this. So for example, we need our data to be private, and we need our model to protect that privacy. It would fall under security and privacy and privacy. You need to be resistant to attacks in some way, or things like compliance. So this is just a good list of things that you can start with, and you can say, what does my model need to do for me? And what are the additional requirements that I have around it? So you can go through these and say, is analyzability important to me? If it is, you will create a QA scenario for analyzability, then you can then test it. If it is not, you don't have to do that. You can skip that one. You don't have to do all of these for every model, but this is just a baseline and a good example of things that we would want to be doing when looking at model components development. So the ones that we identified that were important for Garden Buddy are, we looked at fairness. The one we looked at was robustness to image blur, robustness to channel loss. We have performance, interpretability, functional correctness, resilience, and monitorability. And again, these will be unique for each model that is being created. And so you want to derive from that list of options what is important to your model. And you will then use MELT to create test cases for each of these to validate that they are being satisfied in the end product. So then finally, we have the MELT report. And this is where all of the testing comes together, and you will see whether or not your model satisfied all of your quality attribute scenarios. This is a quick example of what a MELT report will look like. So it communicates test results. The results may lead to renegotiation of requirements or the creation of new requirements. It provides testing evidence, especially in cases where the ML component development occurs in separate teams, organizations, or contractors. So in the case that you would be acquiring a model from a contractor and they required you to use MELT, you would provide them with this report. And so you would have identified all of the quality attributes that they thought were important to this model. You will then have written test cases to validate all of these, and then you will provide them with a report to show them that each thing was validated correctly. And then if they would like, they would be able to rerun these tests, produce their own report, and ensure that the results match up and that they still meet the requirements that they had for the model. And if there are issues in here, then you can go and renegotiate different quality attributes, or you can adjust the thresholds for positives and negatives, and so on. So then we are going to go at the end where we have test code data, and we have our production ready model. So we've had some feedback from early adoption of MELT. Some of the things that people have liked about MELT and they have found have strengths. So MELT forces model developers trained as data scientists to think beyond model performance. So again, when you start with doing machine learning, a lot of time you are focused strictly on the model. You say, I get my data in, I want to get a certain level of accuracy. While this can work and create good models, it does not mean that this model is going to fit into a system as a whole and produce good output within that system. So MELT helps you to realize that larger context and build your model surrounding those requirements. MELT helps to guide the requirements elicitation process, identifying a larger number of relevant model and system requirements. So similarly, from the other side, as a stakeholder, you may not know what you need your model to do. You, again, will say, I want it to identify flowers very well. What that actually means in practice is very different. And so that is why you will use MELT, and it will help you elicit all of these other requirements that could be imposed upon the model that you would not have told the model developers if you did not use MELT. So it helps you structure this conversation and provide a list of information that you should be elicited during these conversations so that you can have less rework. So MELT also facilitates the development and reuse of test code for these requirements. So once you have done all of this work, you have got these requirements, they have built the model. We want to make sure that the model fulfills these things, and we want this to be repeatable. So you then can use MELT to do this development, and you can reuse this test code and you produce reports, and you can iterate upon the model much more effectively than you could without it. So another thing MELT does, it ensures that failures and inconsistencies in model performance are captured during testing rather than finding issues in production. This is not a catch-all, but if you have very robust tests set up and you have identified all of different failure points or requirements for the model that may not just strictly be accuracy of the model at the end, and you have tests running at all times or just during development time, you can identify these issues a lot earlier than if you, again, for example, if you have the model running on a phone and you only test it running on a massive server, and then you deploy it out to a phone, you're going to see issues. And if you elicit these requirements during the negotiation and build the model around that, you will not have that issue in production and it can be addressed during development. So MELT then also can provide evidence of testing, which increases the trustworthiness of ML models. That's another thing that we have seen very frequently is you will see a model or a contractor will present a model and they will tout a very high accuracy percentage, or it has this amazing performance on this type of data. If you were to use MELT or require them to use MELT for these contractors, you can be much more sure that the model is going to be doing what they say it's going to be doing, because they will have a set of tests that they have to run using MELT, and then you can rerun these tests yourself using their model and then ensure that it's actually performing to that level without just trusting blindly the metrics that they give you. So other benefits that MELT provides beyond just test case generation. So as we've talked about a lot, it enables communication and negotiation with stakeholders to ensure that the model requirements are clear, testable, and reproducible. So the model developers should iterate scenario definition with stakeholders to ensure the necessary detail is specified. And again, the most important one here is testable and reproducible. So again, as you're negotiating what you want a model to be doing, you can, again, say, I want it to be fast. That is not testable. Using MELT, you can set up these requirements and set them up in a way that is testable. So you can make sure that on both sides, as the stakeholder and as the developer, that these requirements are being met. Then MELT also can help you elicit better input for ML model design decisions. So, for example, clearly stating and prioritizing ML component QA requirements enables model developers to make critical design choices early in the development process and avoid the cost of rework. Which again, just going back to the same example, if we're deploying on a phone, we want to make the model able to be ran on a phone and not have to go back and rework a very large chunk of the model to fit that requirement later in the development process. And lastly, MELT also enables the reasoning about trade-offs, because using QA scenarios enables the discussion about trade-offs at an earlier point in the software development cycle and forces stakeholders to prioritize competing QAs. So for example, if you say, again, like I want this model to be super fast, but I want to deploy it on a phone, if that comes out during the initial model discussion and negotiation, the model developers are going to tell you that's probably not feasible. And then you can discuss what path you want to take going forward and work out what trade-offs you want to make in order to be able to fulfill all of these different QA scenarios to get a good model at the end of it. So this work is ongoing and we have about 2 years left of the project. So we're talking about some current work and some future work planned. So currently, we are working on improving traceability between the QA requirements and the test code. So the initial versions of Melt, you would set up the QA requirements and you set up the test code, and they were in theory linked, but they were not strictly linked in the code. This is being improved now, and we have this implemented so that when you're making these QA requirements, you can it is much easier to go from these directly to test code, and we actually have test suites templates being auto-generated now. So once you make the QA requirements, it can give you a template for the test suite and the tests that you're going to be wanting to write when using the Melt library. So we are looking to implement many UI and process improvements based on user feedback. So again, the Melt has a front end and also has a library implementation. The UI process can always be improved, and as people use it more, we are making those improvements. And lastly, we are looking at extending the test catalog to include data quality attributes. This is our focus of this year. Our first year was focused upon extending the test catalog to have examples for all the different quality attributes around the strict model requirements such as accuracy and such. And this next year, we're going to be looking at data quality attributes. So when you want to look at your data set and determine whether or not it is going to satisfy your requirements, we're going to be looking into that a lot this year. And then in the future, what we're looking to do is we're looking to identify and generate testing evidence that supports decision-making, repeatability, and if possible, as a stretch goal, model-based software engineering. So just a quick summary of everything we've talked about. So the development and testing of ML components requires collaboration with ML-enabled system stakeholders to elicit the system context and negotiate ML component requirements. A system-centric approach to defining ML components is what MELT is and what MELT aims to be. And adopting software engineering discipline to testing ML components against requirements is another big goal of MELT and why we have all the test cases and the quality attribute scenarios. So, yep, and as we said, MELT is an example of how to instantiate all of these practices in a structured way. So then just some references at the end. We have tools, and we've had several publications related to this work, which we can mention here. So if you're looking for any of the tools, they are all open source and available on GitHub. So Melt is available at GitHub MLTE Melt. We have the tech and descriptors tools. So these were tools from previous work that do feed into the Melt negotiation card. These include much more in-depth negotiation cards, essentially broke into different descriptors. So if you ever wanted to write everything down possible about what you're doing in a model, you can use tech and you can save those requirements, and then you can help use those to inform testing either by using Melt or just directly from using tech. And then we also have other tools such as UnitML, which helps you provide unit testing for ML components by auto-generating them, and then train test leakage, which are available in separate repositories. So Melt is in its own repo. Tech, the descriptors, and the UnitML are available within the CMU SCI repository group. And then these separate repos are available separately at their own developers' repositories. Papers that referenced all of these, we have several. I will not go through all of them. We can highlight this one that received the Distinguished Paper Award at HiRSE in 2022. And then even more, which we then also received the Early Career Researcher Award for this one in the AI for Kane conference. So if you're interested in using Melt, if you would like to talk more with us, my contact information is here. And then my contact information for the team lead, Grace Lewis, who was here today and will open to answer questions as well. She can be contacted here. And contacting either of us about the work will essentially be contacting the whole team, and we can talk about any different type of the work, how to use it, and so on. So with that, I think we will open it up to any questions that people have with the remaining couple minutes.
Thank you for watching our seminar. Please check out the slides on Zenodo linked below and see you next time.